Given similarities with Module 5.2, we'll wrap up Module 5.3 with just two parts. The two-period model, in this case, remember this is additive, and so if up occurs twice, it's just 2 times U. If we have up and down, it's U plus D, and down twice is 2D. And so with this particular framework, we're able to construct the equivalent martingale measure probability of the expected terminal payout. Now, unique to ABM is the lack of easy computations of the probabilities in the sense that the equivalent martingale measure probability of an up move, assuming a constant risk-free rate, will not be the same, because this is simply the S0 times R is the interest amount on available if I invested that amount in the bank, the price of the stock. Well, if the stock goes up, I get more interest. If the stock goes down, I get less interest. And so these probabilities actually change depending on the value of the stock. And hence, the solution to get the right results, one solution that I was able to find is just compute the European style using backward recursion in the same way that we do with American style options. And so we have the two loops, if you recall, in R. We can just apply that to both European style and American style, and it does result in the European style ABM binomial model being slower in its computation. Again, we can work through some numerical examples. If we have a two-period European style binomial, we can compute the terminal payouts on the options as well as the stock, and then use backward recursion to calculate the value of the call and put if up occurs, value of the call and put if down occurs, and then work backward through the tree to get the current option prices. And so with these particular numerical values, I would encourage you to work through them just to gain confidence that you understand the methodology. And in this particular case, we come up with a hedge ratio of 0.5354 and a call price of $13.25. The two-period binomial put, we get similar types of calculations. In this particular case, we have two terminal values equal to 0. Therefore, I don't have to calculate that if up occurs, because I know the price is 0 and the hedge ratio is 0. And then working backwards, the put value is 1037 in this case. Recall, American style means I can exercise early. I'm going to start at the terminal value and work backwards just like we did before. The method for handling dividends, I could use a constant yield. I could use the escrow method. In the escrow method, I'm going to model the stock less the present value of the dividend and assess early exercise at each node. And so if I apply this to American style put option, what we'll notice again, the terminal payout is $20.80 if I exercise early. Based on the ABM binomial model, it's $20.69.8, and therefore I will exercise early. Therefore, the put price today has a higher value. And so just like with GBM, there are coherence conditions with ABM, and they are similar in structure. Basically, the interest earned on the stock, if I put it in the bank account, should be somewhere between the dollar received if down occurs and the dollar received if up occurs. And then the probability condition needs to be somewhere in the neighborhood of a half. The no arbitrage condition is a little different than before in the sense that rather than total returns, it's just the interest that I would earn if I put the stock price in the bank. And then the variance condition, just to make sure that the volatility remains the same, is basically U minus D squared pi times 1 minus pi. Again, just analyzing, why do I have to keep it close to a half? Well, this is the reason why. These results are actually a little more stable than GBM, but the key thing is just keep your equivalent martingale measure probability around a half, and you don't have machine error problems. Generic options, again, we can compute the generic option pricing model by using an indicator function. Again, if we apply the coherence conditions, we can solve for U and D that guarantee compliance with these conditions, and it's very straightforward to deploy these in practice. And ABM, the ABM binomial option valuation model will require backward recursion. The GBM model, we could just simply take the present value of the terminal payouts. With ABM, the probabilities are path dependent, and so the challenge is figuring out what this correct probability is, and that is a significant challenge that I've yet to figure out. However, we can use backward recursion. And so basically, if you think about a 9-period binomial model, it's just a matter of starting at the end, working backwards, just like we did with American style, but we would do it with European style. Just as with the GBM model, American style, we have to test for the binomial value, the early exercise value, or the intrinsic value, and the lower boundary condition, making sure that we select a maximum of those three, which is what an investor would do. Dividends, this is a unique insight for the ABM binomial approach, is that if we have a discrete dividend amount, and so on the ex-dividend date, the price of the stock drops by the dollar dividend amount, if you'll notice, the tree easily recombines. And this is a powerful feature of the ABM model that is worth exploring in more detail if you're trying to build out different option valuation models. Again, we review digitals or binary options. I don't want to spend too much time on this, and so we have explored the additive binomial model, addressed dividends, looked at some digital options, European and American style, and looked at a variety of plots. And we'll turn briefly now to look at the R code. The R code is very similar to what we looked at with the GBM binomial model. We put the functions into separate files. And so if we look at the European style ABM, there's basically a single function that computes a variety of different outcomes. Now, just for fun, we produced a structure that will return the call value, the put value, the digital call, and the digital put. The reason for this is it takes such a long time to get through the backward recursion, we might as well compute all of these values. And so if we run this program, it produces the lower bound, upper bound, present value of $1 in this particular European style model. If we introduce sort of the canonical example that we've been using for quite a while, 500 time steps may take a little while to run, but we can look at some basic results. These are the footer information. It's very helpful to have available. And so if we calculate the European style, plain vanilla, call lower bound, call upper bound, and put lower bound, put upper bound, and then we can compute the value. And so what we'll notice is when we ran this particular European style model, it produced a call value of 1420, a put value of 935, a digital call of 52, and digital put at 42. And so I can then import out of the structure the call value, put value, digital call, and digital put, and then print these out. And so if we'll notice the present value, if I add a digital call with the digital put, that difference is going to be the same as the present value of a digital payout is going to equal to a digital call plus a digital put. And so we could run a variety of different outcomes in this particular model. This will probably take a little while to run because it's 500 and it's European style. And so I'm going to pause this and come back when it's finished. Well, the code is now finished running, and so it produced a whole set of values. What is produced next is a variety of different plots. And so if I make the plot area a little bit bigger, it's easier to see, and hit that and look at the plots. And so this is the European style binomial values versus the lower bound and the upper bound. If I wanted to look just at the time value, I could run that piece of code. And again, we noted before that this was symmetric, and with puts we get the same type of diagram that you would expect, except for this time the log normal, the distribution assumption is replaced with the normal distribution assumption, and we have the put time value, and a variety of other plots could be produced. The routine that based on number of steps. Now this particular snippet of code will take a while because it runs the binomial model across a minimum to maximum number of steps by step size. And so the European style model is fairly straightforward, but it does require backward recursion. The American style model also requires backward recursion. And in light of that, the length of time that it takes to run these option valuation models, we go ahead and capture all 4 values and replace it and return a vector basically of 4 outcomes. So I'd encourage you to spend some time with this code if you're interested in building out an ABM version of the binomial framework.